Okay, so we continued the lecture last week. So last week we consider an operator P. E is equal EM, put it all the way in, and there is Q, XD, all the way DN, mass, and the same side with the their commutator equal 0. So this implies there is a PC binomial equal FPQ, okay, such that FPQ equals 0. So here we assume rank 1. Let's and the N, okay, a corporate. Assume this. Okay, so in this we know if PQ, okay, is a smooth point of the spatial curve. Okay, then we know there is a unique. We call eta. Okay, so this eta is unique. PQ function of x. Okay, so this is a common 0 of P minus P and the P minus Q minus Q equal to 0. Okay, and similarly, if this is smooth point, then we have the C. Okay, so function of x such that is a common common 0 of the P adjoint must be equal adjoint Q equal 0. Okay, so we have these two functions. So the main theorem is want to prove actually eta and C can be considered fixed x, can be considered a function of PQ. That's the function defined on the spatial curve. And we want to prove those two functions has essential singularity but PQ at infinity. Okay, so to prove this, we last time we consider operator if I substitute P by operator P and then divide these two operators, we have the factor P and this remainder can written as in this way. So this remainder is the leading term is psi and the order Pn minus 1 and the second term is psi 1. And also we can do the adjoint of P and do the same thing. So the leading term is a 5 and this I call this equation 2. And then we also can do fixed P and replace Q, small q by operator Q. And we divide it, then we have the same thing. So it's 1, 2, 3. So we have introduced function psi 1, 5, 1, and the chi, and the function chi. Okay. Last time we proved chi actually equal negative cosine. So this is important. Okay. And also we also prove this remainder, this term remainder. Okay. Without this factor, just consider this term. If I assume PQ is a smooth point, then I have define eta. As I still there, right? At eta, and consider the first operator, first order operator, B minus eta prime. This prime means derivative with respect to x and divide by eta. And I multiply this remainder, then surprising is this one equal cosine times the original p minus p. And also I have the same thing. We can do the transport p, and then I have also multiply p minus the first order, the simplest order, multiply the remainder, then I get the phi times the transport minus p. So I call this phi. Okay. So at the end of the last lecture, I say I want to prove cosine and the eta. This theorem 1, the first part of theorem 1 is the cosine times eta inverse. Okay, this is the ratio cosine and eta. Actually, is also common zero of the transport, not the original p. The transport adjoint of p minus p, and the adjoint of q minus q. And if I starting from the phi, so this is phi is in the equation 2, right? This is do the transport, and then find the adjoint of the transport equation. Then this will be common zero of the original p and the q. So we want to prove this, and then we want the second part is we want to prove cosine actually equal phi. This is for any PQ, not necessarily smooth. Okay. For any PQ, on the spatial curve, we have a phi equal cosine. So consequence, this eta, fixed eta, I can normalize cosine by the phi times eta minus 1 equal this cosine. Okay, so this normalize this, and this is the first part of B. Okay, so we want to prove theorem 1. So let me give you a proof. So this proof actually is not so hard. We use the equations 4. So let me use equation 4. So I do the adjoint. Adjoint for the on the both sides. For 4. So what we have? We have the side this adjoint, and then I have adjoint. So adjoint D is minus D, minus E prime D. Okay, and the time P minus P transport adjoint of P minus P and the cosine. Okay, so from here, from the left hand side, it's easy to put eta Okay, inverse. If I put eta inverse, then I know the minus d minus eta divided by eta. This guy equals 0. Okay, so this implies besides sin eta inverse is a 0 of the transfer P minus P. Okay, so this for the first part. For the second part, we do the same thing for the equation 3. Okay, so for equation 3, we also have the same identity for 4. So this means I have a D, so similar to 4. Well, from the equation 3. From the equation 3, I have let me see. P transport. It's P. So I transfer this guy. Yeah, so from the equation 4, right? Okay, I can do the same thing. So I have the chi 1 minus d minus eta prime. Chi eta. This is chi. Okay, chi dn minus 1. This d4 chi q, okay, minus q. Okay, they are the from 3 I can do the same thing as the derivation of the equation 4. So I have this equation. Okay, I call this 4 prime. Okay, then do the adjoint. For equation 4 prime. So I have what? I have a chi transfer of chi and the chi this is minus d minus eta prime divided by eta. Is equal transfer minus q and the chi. Okay, so this implies chi okay, so this implies chi acting on eta inverse and acting by the q transform minus q. This equals 0 because minus d minus eta 1 divided by eta acting on eta minus 1 equals 0. Okay, so we have this. So this implies minus sine eta inverse equals chi eta inverse is a 0 of q transform minus q. Okay, the first identity following from the last time we proved on this identity. Okay, so we prove the first part of A. Okay, so you starting from the transport P, then we can do the using the equation 2 and the 5 So we can prove phi times C inverse is also 0 of these two. So similar we can prove. Okay, the second statement of A. So this is the first part. This is part A. Okay. So now I want to prove they are the same. So from part A, we know the psi eta 1 is a common zero of these two operators. The common zero of these two operators is C. And C is unique up to a up to a factor. So this equal by A is equal to C. Okay, and similar we have the cosine I C equal another C cubed. This is eta. Okay. So no, this is phi. Alright. So this implies C equal phi, a constant C, a constant phi. So the constant is a constant is independent of okay. So this constant is a constant independent on X. Okay, so I want to prove B. So to prove B, we need the following name. So this lemma is said. The first part of this lemma say this precise as a function of PQ. Okay. This is a polynomial of PQ with weight. So this phi PQ can be written as dimensional CABX IPA QB. Okay, with AB MA plus MB less than 2G. Okay, so this is the first part, and moreover, CAB X equal 1. If MA plus MB equal 1. Okay, so we have the lemma A and the B. We write a B. we do not use here, we do not use this, but for interesting comparison with phi, we write the phi 1. So phi 1 is PQ. It's also a polynomial of weight 2g minus 1. So I write this T hat AB. And this is the A, MA plus MB. That's the 2g plus 1. And the leading term is also PA0, QB0. But such that T plus AB and PA QB. Okay. Now is MA plus MB less than 2G. Okay, so the leading term also equal this guy, equal 1. Okay, and where PM A0 plus MB0 equal 2G plus 1. So the proof of the lemma is very tedious. So I want to present here. If you are interested, you can look at the notes. The lemma 2.6 for my note. So we don't prove this. So let me erase this. Okay. So now we come to the proof of the part B. So similarly, we have the B beside. This function is also weight of 2G, and the leading term is the leading term. This is the PQ, PA0 head, QB0 head, and the plus summation of CABX, PA, QB. Okay, all the weight is the weight with weight MA plus MB less than 2G minus 2. Because 2G minus 1 is not the lattice. Okay. So listen. And let me use the hours is 5 PQ. X equal some P A0 Q and B0. Okay. Plus dimension of the C ABX. Let me use this head. Okay. CABX PA QB with MA plus MB less than 2G plus 2. Okay. So here M A0 height plus B0 head equal MB0 head equal 2G. The weight is 2G, and this weight also 2G. Okay, but 2G at the level 2G, A0 head and B0 head can be uniquely determined by the 2G. So this implies A0 head equal A0 B. Okay, now we have the constant. Okay, the constant. This is the so we use the constant. So by the above, we know the constant. On the other hand, we know psi PQ equals some constant ID YPQ X. Okay, so this is D is a constant independent of. So comparison the leading term. So we have the D in front, D equal 1. So we prove the second part. D. Okay. So the theorem 1 is the first major step. Now okay, so we have equation 4 and equation 5, right? So now I suppose the F, the P, we call it P minus B equal to Dm plus mu1 Dm minus 1 plus mu2. Okay, so the corollary of theorem 1. So we have the final result. The psi prime plus psi 1 plus phi 1. Okay, plus phi 1. Phi 1 is here. Right? So the next term is the psi 1, Pm minus 1. Psi 2, Pm minus 2. 2 is minus 3. The psi P minus 3. And this is 5 is psi 1 Pm minus 2 plus psi 2 Pm minus 2. Henceforth, okay. Then I have the psi plus phi, the derivative phi with respect to x. And the phi 1 comes from the equation 5 and the psi 1 here. Okay, this is equal 0 and the psi pi mu2 psi plus psi 2 minus psi prime minus mu1 psi 1 is equal phi 1 psi 1. This I call equation 6. This I call equation A. Okay. Of course, so how to apply? So derive this. So I use the equation 4. So I can compare the coefficient of dn minus 1 and the coefficient dn minus 2 of both sides. For example, dn minus 1 is coming from this part and the d derivative, then d acting on this, so cosine 1. Okay, and then together. So I have if I compare them together, I have cosine prime plus cosine 1 minus theta prime theta. Sine equal mu1. Okay. So this part is the coefficient dn minus 1 in the left hand side. Okay. As I told you, because d differentiate this guy, if you get the first term. Okay, if d do not differentiate, then you just differentiate this side, you get the cosine 1. And this term times you get a certain. And the leading term of this is the dm minus 1 times mu1. So this together, I have this mu1. So I have this. Okay, so this one, first one. And then compare dm minus 2. So this is very complicated, but it's also very easy to compute. I have cosine 1 prime cosine 2 minus theta prime divided by theta and prime cosine 1 is the mu2 cosine. Okay, I have two equations. Just compare the coefficient of dn minus 1 and the dn minus 2. And also I can compare this dn minus 1. Okay, so I have doing the same thing as the first equation here. I have the cosine prime. Actually, I should write this is the c phi, right? Plus phi 1 minus cosine prime theta, and the cosine is 1, and the mu 1 is c. But I know by c equal 5, so I replace this cosine. Okay, so I have 3 equations. So I can cancel out the mu some terms. Okay, then I get these 2. Okay. So this is a basic equation. So what we have? So this basic equation, and recall, I have the cosine equal. Okay, I have this equation, call this 10. I have 3 equations together. Okay. So let me write down the consequence of the n to 10. Okay. First, the lemma. This lemma says it's a polynomial with 2g. Okay. So first, I have the consequence of n to 10. And the lemma over there, lemma A. Okay, so first, Yes, I have 3. So I have for any x, remember the domain of definition of x is I. Choose all the coefficient operators are smooth, defined in this interval. Okay. So I have cosine PQ x equals 0. Since the degree is 2g, so has the S 2g solution. Okay. So this 2g solution, of course, this counted with the multiplicity. Okay. So in the following, we assume the spatial curve is smooth. And the hypothesis H. So the hypothesis H is say is an interval, a subinterval. J of x. Okay. Such that you put x in J and cosine PQ x equals 0. Cosine PQ. Then we assume, then we have the derivative of cosine with respect to x. P cosine PQ x. This is not 0. So let me assume this assumption. Okay, so let me make a remark about this assumption. So we have checked this assumption H is false, is true if m equal 2. Okay, this means so if the order of P is 2, then the x, the capital X, the explicit spatial curve actually have an elliptic curve. And we can prove this hypothesis always true. And we expect, so we expect the hypothesis H to be true in general. Okay, I haven't checked this, but I believe it's true. Okay, let me assume this. So throughout the discussion, that from now on, we assume X is smooth, okay, and the hypothesis S. So let me list the consequence under consequence of 8 to 10. This means we are going to do the following. 8. Okay. Then beside PQ, so I say they are 2G solution. Okay, they are 2G solution. So I ask alpha s and beta s. And so from the equation 9, imply what? Imply either psi 1 equals 0 or psi 1 alpha s. Okay. So now I assume this if this is 0, but I assume this not 0. So the alpha s and the common fact 0 of the fact is and the such that okay. So let me assume this. So how many of so assume there is s equal 1 up to g. Up to g. Then we want to show T1 equals G. Okay, so similarly, psi alpha s beta s x and psi phi 1 equals 0, but psi 1 is not equal. Okay, so this s is from 1 to G2. Then okay. So this first property we want to prove. Okay, B. So recall here 10. So you psi equals 0, then I have the cosecant, either cos equals 0 or eta equals 0. Conversely, if cos equals 0 all eta is implied to psi equal 0. Okay, but from the assumption here. Okay. So obviously this function cannot have 0 vanish simultaneous at the same point, because this is directly not 0 to x. So similarly, we have if this equals 0, either this or this equals 0, but exclusive. Okay, so we can guess. So here is, okay. So that's the common 0 of this guy. So that alpha s is a common 0 of psi and psi 1. Okay, then so this is s equal from 1 up to t. So then alpha s, beta s, x are the zeros, the common zeros, the zeros of E, PQ, X equal. Okay, so eta as a function of PQ on X, their 0 is just the same as the common zeros psi and psi 1. Okay, so this is the second property. Moreover, okay, so now with moreover, okay, the divisor dx defined by the x is a non-spatial okay. I will tell you that in the later lecture, maybe in lecture 3, I will tell you what we mean the non-spatial divisor. So this is a terminology from the Riemann surface. I will tell you what it is. Okay. And this is very important. So what I mean is so this contains the meaning alpha s. So not only 0, actually they are simple 0. Simple 0 beta. Okay. So this P. And then I want to C. we want to prove C is the normalized normal common zero is eta PQ x 0 defined by eta PQ x. Okay. So this function consider of is for any fixed pair. Pair, right? Okay. Is Melmore function function on x, okay, such that the zero divisor the whole divisor are non-spatial divisor. This is come from B, and it's essential singularity. Of x. So for ABC, so this is a major the major property of about the operator P. Okay, so let me prove 1 to ABC for you. Okay, so let me define. So we have definition G1. G1 is the common zero of the OS, okay, and the phi 1 is the under common zero to psi and to psi 1, but the phi 1 is not zero. Okay, so to prove this, I just tell you the strategy. So we want to prove first, step 1. Are you applying the residue theorem? X. Of course, X. Let me speak. Proof. We show that they are omega alpha s beta s. So now we fix s. Such that dimensional alpha s a beta s b omega alpha s beta s s equal 1 to G1. Okay. I have s equal 1 to G1. This equals 0 in the way MA plus MB less than 2G minus 2. Okay. And equal minus 1 if MA plus MB equal 2G minus 2. We have, sorry, let me recall. This meaningful because the 2G minus 2 is always nothing strong. Remind you this. So how many equations of this? We know the largest number, largest point. Okay. Then the AB, right? Number largest point from 0 to 2G minus 1. Totally have the G, okay, the number as the G is equal to the number. Okay. So I have, so from here I have the G equation. Is unknown. One. So unknown is unknown is W alpha is beta is. So this number is one. Okay, so I have this and step 2. So I want to call it for this equation. Let me call this 11. So I can prove this equation 11 has a solution by using residue theorem. Okay, and step 2. Step 2 is I want to prove the solution of 1 or 11 as at the most one state. Once I prove this implies okay, G1 greater than T, greater than or equal G. Okay. But we also can do the join 0 to psi and phi. and the other the phi 1. From here I get G2 also greater than G, but G1 plus G2 is equal to G, so I will imply G1. Okay, so this is A. So how to prove the second part? So I have derived the following identity. So this one is a step. So step 2. Follow the identity. One PQ. Okay. Is equal some function for rho x. And this is equal summation of the FP P beta S x. The time omega alpha s divided by P 减 alpha x. S 双关的 P 1。Okay. So I think the 12 is essentially very important, but the relation not very hard. So from here you see, because you have two solutions, G1 and G. You have the alpha omega has two solutions. So I have the other is the S1 T1 times FP beta Sx. And I have omega A. Divided by P Okay, so this is easy to see at the singularity. This guy should be equal to this guy. Okay, so this is quite unique. Now I want to prove step 2. So after step 2, I get a G1 equal G. So I come back to now I tell you how to prove step 1. It's very. I have used a big force to raise and up down, up and down the breadboard. So this exercise makes me now feel hungry. Okay. So let me prove 11 first. So this is just using very simple idea. Okay. So now, how to prove this? Please. Maybe I use the breadboard. So I can consider all the way AB. I consider the one form omega called omega AB is equal, okay, for cosine FQ, okay, and the PAQB. And I want to buy one Q. E. Okay. So of course, if FQ okay, if FQ if it is equal 0, then I use the cosine same thing here. By 1, I use this phi, this P, PQ. And the PQ are always smooth, your X is smooth, so either this false or this false. Okay. We know in general we have the P Q and Q. So I use the negative. Okay. Then the simple pole is the pole of omega AB. It happen at the side beta QX equals 0. But okay, find one PQ X 9. So this means the PQ in R is okay. So at the R S beta S, we have a simple pole. Okay. Yeah. So hence this omega AB, there is a residue. The residue is happen at the PQ equal alpha S beta S equal 1 to 1. Okay. So at the ratio, the total ratio, let me write this as the PS. So the ratio of this guy is equal PS AQSB. And the time and the ratio of this side. y1 side and f q dq and ry. Okay. So this exactly is very true. The other, if this equal 0 and y1 also 0, then they cancel out. Okay. So it's not the pole. So pole only happen at here. Then and you can compute the infinity omega AB at the infinity. Omega AB is smooth if weight MA plus NB is 2T mass 2. Okay, and has the ratio. Okay, ratio omega AB has a simple pole. And enter the if MA plus MB less than equal to T minus 2. So we can multiply constant C here. Okay, to make the at the infinite ratio is equal minus plus 1. So all the summation, the ratio equals 0, then give you this equation. Anyway, so this ratio is 0. Okay. Okay, so this at the infinite is not difficult to compute by using why I already tell you the lemma is the weight is 2G. Okay. Okay. And the phi 1 is 2G plus. I already 2G plus using this. This weight is 2G. Okay, so we prove the first step. The second step, I want to prove this identity. Okay, this identity is kind of limiting. So let me just sketch it quickly. Okay, let me see what. So we choose the PD or Q0. And the beta 0, let me define this is a function of x. 0, E0, Q0. Okay. So I want to use the equation I erased equation 1. Equation 1 is let me read FPQ. This is the T, right? Operator time T mass T, Q mass Q, and plus the sign T n mass 1. I have the T mass Q. Okay, I use the equation 1. So let me taking on D at both sides. So I have if I use this, then I have Okay, so I just multiply this. Okay, then I acting on the function eta 0 x on both sides. Okay, so I acting on this on both sides, then I have if I acting on here, for example, I have the d minus eta prime eta, right? And the eta 0, then I use f p 0, right? This q eta. Okay. And this equal. I use eta 0 acting on this side. Okay, I have the d minus eta prime eta. Okay, and the t time and the plus. I using this guy time is this equal to psi p minus p. So I have so p minus p multiplied is the same as here. So I have p psi. Okay, and the totally is the p minus p and the q minus q. So acting on eta 0, so this guy is equal f1. This is q minus q. Eta 0, right? This is this q acting on eta 0 is the f eta 0 is q 0 minus q eta 0. And acting on this is p 0 minus p. So I have this. So totally, this side I have the p 0 plus p and q 0 minus q eta 0. I have this. Okay, then I can cancel out. I can divide this on the both sides. So I get what? So I have fp0 q divided by p0 minus p q0 minus q. And b minus eta prime divided by eta. Acting eta. So this is this side. Eta, this is constant. I take out, so this is. And the left hand side is the d minus eta plus eta. And then I have t plus eta. Okay. Okay. So before eta prime, I have set kind of the psi prime plus cosine 1 minus eta times eta. The cosine is equal to mu1. So this is the corollary of 7(1). Okay, so now I put the alpha, I put the P alpha S PQ equal alpha S and the beta S. Okay. So I have this number equal 0. And this equal 0. So what I have? I have an eta prime, eta pi cosine. Okay. So actually I should write this cosine pi eta. This is exactly equal to cosine prime alpha S beta S. And assumption H is 9. Okay, so this implies cosine over Q under S beta Sx. They have the same, this line equal. Okay. I have the first identity. So this tells you we cosine equal 0 implies. So they are the same. Cosine equal 0, eta equal 0. This from the equation identity 10. Last time we have 10. Okay. Okay, so now I use this apply to here. So what I have. Okay. Okay, now from this I multiply cosine. Okay, alpha S beta S. And the P replaced by alpha S and the Q beta S. So if I multiply cosine, then I have cancellations. First, this time derivative equals 0. Okay, so I just cancel out. So this term cancel out. And this one I have the eta prime eta cosine. So maybe you add the alpha S beta S. And the time eta 0. Okay, so this is P, this is A. And if I multiply cosine here, this term complete 0 because cosine is equal 0. And we have the this term. So I have this is E minus prime cosine, right? Eta cosine. Okay. And then I have the T plus cosine. But cosine equals 0, so I erase it. Okay, so both sides I have this. Hence, this is not 0, I can cancel out. Okay, this is not 0 here. So cancel out, then I get the following. FPS beta S divided by P0 and alpha Sx. Q0 beta Sx. Okay. And I have only eta 0x. Remember, because this term cancel out. And this equal T. alpha s beta s x. This operator, right? This operator acting on eta 0. Okay. So I have this equation. Okay, now I multiply omega sx. Okay. So I have if I multiply omega x here, this side is just easy, right? This is sum of the s equal 1 to g1. So the f multiply it and the summation. Okay, from s equal 1 to g1. Okay, so this is the p0 minus alpha sx. And time q0 minus beta s. And the time eta 0 x. Equal multiply this. Okay, alpha s beta s. Time t alpha s x beta s x. I have this identity. And then the operator t satisfies the following. The operator t so operator t has a weight is the okay, let me write this. The operator is equal. If you go look at the plural lemma 2.6 in my notes, then you can see this is the operator is A, B, J, P, A, Q, B, and D, J. Okay, where the weight of P, A, B, M, A plus M, B plus J always less than 2G minus 1. Okay. So if the differential G greater than 2, then MA plus MB less than 2G minus 1 minus J. So this is 2G minus 3. Then remember I put the alpha s back, so P represents alpha s beta s and the multiply cancellation of this. So summation of them together, all the coefficient dj equal 0. Okay, so this implies if I write the t equal the first term t plus rho x. Okay, and so no, if I write this, I mean if I am writing so summationally the left hand side. So this part, the right hand side is only t plus some. We can prove is rho t plus x. First order, second order, higher order, all cancel out. So this is eta 0 x. For eta x, so this rho x is the coming from the 0 coefficient. So this is weight 2G minus 1. Okay. Okay, so this is, and from here it's easy to see is this just minus eta 0 prime x plus rho x. So you divide by eta. Divide by eta. So we get the identity term. Okay. And of course, P0, Q0 is the PQ here. Okay. So we prove the identity term. Okay, then it's easy to see, right? If we use integral of x, you integral x both sides. Then this part we get what? We get the log eta pq x eta pq x0 integral of all this. So eventually this equals some function ex and the time exponential minus integral this part integral this one x. And if I take PQ goes to infinity, so you compute this PQ at the infinity, okay, and actually a lot of cancellation. From here, I don't go detail, and we can see this is from here we assume approved as PQ tends to infinity. The identity here star has the essential singularity of eta PQ x. So this is eta x. Okay, so we proved our first major theorem. And okay, now time is up. So I want to tell you is for the second part I already written on the lecture note, so I skip it. Okay, and actually in the lecture 3 I will come back this kind of problem to solve the PQ from the information of spatial curve. And this is the one try to solve PQ in terms of the Riemann theta function. So there is a general idea coming by the many people say to polynomial retriever is. So I just name a few of them. Okay. So this is the we will continue for lecture 3 for the second order ODE. And okay, so I want to tell you is for our seminar, for our series lecture, we start today. Okay, and we will come back on September. So during summer we don't have the seminar. Okay, so do you have any question? You have no question. Okay, I will revise my lecture note on the second lecture later, and if you want to know more detail of the calculation, in particular some result we didn't prove here, so please go to see my notes revision. I think I will put there this week or the next week. Okay. Okay, so we will come back on September. I will inform you when we I think around the end of August. Yeah. So tell you when But in any case, we will lecture our the lecture 3. The lecture 3 will first we face the guest speaking, ecstasy, and important book. And the second is some paper, okay, by the paper by Tupori. This is it's rocket survey. This for lecture 3. Okay, so see you on September. Thank you for your attention.